we may as well start. This lecture is in fact an introduction to the soil root system, and the reason it was formulated as such is that the next round of lecturers, Stefano Manzoni and Kari Jensen, are going to be discussing a lot of processes in the soil plant system. And while I think we have done a decent job at covering the processes in the plant, I thought we might as well do an introduction to soil processes. A lot of the students who have attended the summer school this year come from a more meteorological background and have not taken a single soil physics or a soil science course. And so I thought it would be most constructive to give an introduction to the soil root system, but still have some level of depth that you would not typically see in a textbook. So with that, we'll start the lecture on a review of the soil root system. And the first thing that worth mentioning is that Leonardo da Vinci in the 1600s stated that we know more about the movement of celestial bodies than about the soil underfoot, and that probably statement is still correct today. Our knowledge is much deeper in terms of the Big Bang, how the galaxies were formed, etc., and we are still struggling in terms of very, very basic problems in soils that we still do not have clean answers for. So despite the statement being in the 1600s, it still applies to the state of knowledge today. Now, as a brief introduction, why are soils so complicated? Soils are, how should we say in the language of today, are multimedia. Yeah? So there is water, there is solid, there is air. And so typically, it is a multimedia system. Water is moving through pores. Air is diffusing also through those pores. The solids may consolidate, may expand, may shrink, may swell. So it's quite a bit of a complicated system. And then when you add roots to this mix, it becomes even messier because the roots also are not static. They grow, they die, you know. And as a starter, how do we quantify properties in the soil? Of course, because the soil has all these phases, air, water, and solid, the obvious thing is to start thinking about a volume-mass relation for this composite system. And to do that, what is often done is you basically do not care about the arrangements of the soil particles in those definitions. You don't care about the size of the pores or anything. You just care about volumes and masses. So you break up the soil into its constitutive terms, air, water, and solid, each having a characteristic volume and a mass. And then what you do is you define bulk relations between the volume and the masses in this system. So the bulk density of the soil is often defined as the mass of the solid divided by the total volume. So the total volume being the sum of the air volume, the water volume, and the solid volume. The porosity of the soil is another quantity that is used extensively, and that is basically the volume of the air and the volume of the water divided by the total volume. So basically anything that is not solid is considered to be porous, and hence either allows gas diffusion in the case of dry soil, or is the maximum soil moisture content, as we shall see in a minute, for saturated conditions. So what do we mean by saturated conditions? It means that the volume of water occupies all the space that can be filled, basically, in the soil system, and that includes the air volume and, of course, whatever the volume was occupying. So the degree of saturation is the volume of the water divided by the total pore space that can be occupied. So anything that is not solid is basically available either for water movement or gas diffusion. Then there is the air-filled porosity, which is the volume of the air divided by the total volume. If you look at studies of diffusion of gas in soils, say like oxygen diffusion or CO2 diffusion in terms of respiration, this is the most important quantity that you would see because it dictates the space at which molecules in the soil system can diffuse. For us, the analog to this quantity is going to be the volumetric soil moisture content, which is the volume of the water divided by the total volume of the soil. So that's basically the key state variable that describes the water availability in the soil system. By no means this definition is unique. If you look at the engineering literature, especially the pavement design literature, they like to reference everything to the solid volume rather than the total volume. So you might see analog definitions that are all anchored on the volume of the solid rather than the total volume. Okay. So this is basically the bulk properties of the soil that you see. And the reason those are actually popular is that they're also easy to measure. How do you do that? Well, you go to the field with a sampler. This is the shovel experiments now, yeah? You dig a small hole, you take your sampler, and typically the sampler will have a fixed volume that is associated with it. And so you dig the sampler into the soil by hammering, pounding a little bit, and then you extract basically a volume of soil, and there are usually putty knives that you stick on the sampler, so you could then subsample the volume that you have taken to avoid boundary conditions, because you jump probably on the sampler and you disturb the soil. And then you take a fixed volume of soil. So the total volume of soil is easy to measure, and often with these samplers, it's about 60 centimeters cubed. Then you weigh the sample, yeah? And then you take it to the lab, and you bake it for 2 days in an oven. You evaporate all the water, then you weigh it again. And so, of course, the measurements that you get allows you to compute the mass of the solid, yeah? The mass of the water, but if the density of the water is 1, you have also the volume of the water. And you could also separately measure the density of the solids. So if you know the mass of the solids and the density of the solids, you could calculate the volume of the solids. You know the total volume, you get the volume of the air. And if you ignore the mass of the air in this problem, because the density of the air is at least 1,000 times smaller than the density of solids or water, that allows you to calculate all the terms in this diagram. And hence, all these quantities then can be obtained. And you might say, from a hydrologic perspective, why should we care about the volumetric soil moisture content, especially near the surface? I mean, in terms of the global water cycle, this is trivial. I mean, it cannot be measured, no? If you think about the volumes in the ocean, the volumes stored in ice, groundwater, why should we even bother with this? It turns out that a lot of life depends on this little bit of water, okay? So that's why we care. How much effort is going into it? Huge amounts of efforts. The recent NASA project that took 10 years of engineering development and about $1 billion to fly a satellite to measure soil moisture content from satellites is one good example, and they still cannot get it. Okay, so just to show you how challenging it is also to deal with the soil system. They had no problems figuring out stuff in the Hubble telescope, and so getting volumetric soil moisture content has proven to be a major hindrance. So that's why it's difficult. These are some of the challenges that people have to face. Okay, now on the theoretical side, the fact that the soil system is actually a composite system makes it also even difficult to apply ideas from continuum mechanics or even statistical mechanics to it. Often than not, we think that there is a sort of representative elementary volume in the system, and that is literally stolen from statistical mechanics and fluids, how you go from microscale to macroscale. So often, if you think about the density of a fluid, if you go to subatomic distances, if it happens that your control volume is that small, you may be hitting a part of a molecule and a part of nothing in between. And then, of course, as you start increasing the scale of your control volume, you will have more and more molecules embedded in your control volume. So the density becomes less and less oscillatory, because now whether you include one particle or not makes a difference. Okay? And then after a while, you reach a certain scale where you have enough, basically, particles. And if you increase the scale, you're increasing a fixed number of particles with them. So the density of the system becomes almost independent of scale. But if you keep increasing the scale, other things, now impact the density, like temperature or salinity or pressure gradients or whatever in the atmosphere. So the idea is that, yes, if you are dealing with continuum mechanics, we can actually define over a wide range of scales, yeah, a representative elementary volume that is independent of scale. Now think about that picture in the case of soils. What does that mean? How big should our representative elementary volume be to achieve quantities like volumetric soil moisture content or bulk density that is independent of the scale? Not very promising, no? Not very promising at all. But that's the essential machinery that we have to deal with soils. Is that making some sense or not yet? So there is a huge debate in the soil science whether the representative elementary volume actually holds. Does bulk density or soil water content become scale independent at some range of scales? And if so, at what scales they are? And more important, when we talk about point equations in continuum mechanics, In the case of continuum mechanics, we know that we are thinking about point equations where the density is defined, the viscosity is defined, and so forth. In the case of soil, what does it mean to write a point equation when you have an aggregate that is 20 centimeters big, you know? So all of those are issues that are often not dealt with in textbooks, but since this is a graduate course, I think we should be honest about them and bring them to focus, yeah? And I have to say that the machinery that tries to deal with these issues is what we're going to end this lecture with, and Stefano is going to pick it up this afternoon from the ending point here. So believe it or not, there is coordinations among the lecturers. Okay. Okay. So as I mentioned, these issues will not be explicitly treated in this lecture but we will provide a little bit of guidelines about how to perhaps think about them down the road, and Stefano's talk will consider them in greater detail. So save all the questions to him, not to me. Okay, so now if we accept the representative elementary volume idea, and we think that we can still define a volumetric soil moisture content that is independent of scale, and let's even assume that we can write a point equation for soils, whatever that point equation means. So at this stage, we're going to assume that, yes, there is a scale that we can write a bunch of equations on, okay, basically. Whether this scale exists or not, I don't know, but let's assume that it exists for now. And basically, you could write a conservation of mass equation in a continuum fashion by simply stating that in a soil system, so this is the ground surface, you take a layer in the soil and you say, well, if water enters this layer and water leaves this layer and what is entering is not equal to what is leaving, water has to be stored somewhere, right? And if it is stored somewhere, it is going to be stored where? In the pores, okay? So basically, the imbalance, yeah, from the flux in minus the flux out, which is here, is going to be responsible for changing the volume of water per unit volume of soil. So that is basically our continuity equation or conservation of mass of water. Notice here that we have not yet introduced any exciting stuff like roots, okay? But we're going to come to that later. But let's start first with the basics. Okay, so this is one equation with two unknowns, right? Which is often the case in those problems, whether be it Navier-Stokes, whether be it open channel flow, whether be it water movement in soils. The two unknowns are volumetric soil moisture content that we are trying to model often, and the flux of water. Okay, so mathematically, to close this problem, we need a relation between the flux and the volumetric soil moisture content, and that's the headache, okay? So how do we do that? Often than not, you might see in textbooks that there is some analogy between the law that we're about to cover, which is Darcy's law, and other transport laws in nature and in physics. So for example, you might see Ohm's law, where the current or the flux of electrons, if you like, is proportional to the electric potential difference, and the proportionality constant would be the inverse of resistance. Fourier's law is pretty much the same thing. You establish a temperature gradient. That temperature gradient causes a certain heat flux, you know, so you increase the temperature, you increase the kinetic energy of molecules or the total energy of molecules. They bounce into each other and heat can move at the molecular level, but at the macroscopic level, that's what you get, a flux proportional to a temperature gradient, and the proportionality constant becomes the thermal conductivity. Fick's law of diffusion is the same thing. You could still get mass movement without moving the bulk fluid, yeah? So if you have a box, you separate the box into two compartments, you put ink in one compartment, you remove this separation, ink will move, yeah, from regions of high concentration of ink to regions of low concentration of ink. And that movement happens despite the fact that the bulk fluid is not moving. So that's a mass transport driven by concentration gradients. And of course, we can always convert concentration to some equivalent energy potential. And so all of those can be actually written in terms of energy potential. And often than not in textbooks, you would see that Darcy's law is the same thing. The flux of water is driven by an energy gradient, and the proportionality constant in the case of unsaturated flows, so there is air in the soil system, is given by a hydraulic conductivity function. But there is a fundamental difference. The previous laws had no issue with the representative elementary volume. Okay? This one does. Okay? This one does. And so there is a big difference between the two. And the challenges that it took Darcy to get to that point are not trivial at all. Even though in textbooks you would see a gentle reference to Les Fontaines Publiques de la Ville de Dijon in Paris, 1856. Let me just say 3 things about this. First, this is a 680-page document. It took 3 years to review. It encoded all of knowledge of Darcy in that document, okay? Because the guy actually was suffering from health problems at the time, because he was an engineer, so he was supervising the construction of a pipeline when he had an accident. And since that accident, he's been suffering health-wise. So he knew that Les Fontaines, as it is called in the groundwater literature, affectionately, you know, so you don't need to say anything more, just Les Fontaines is enough, is basically a reflection of the fact that he tried to put everything he knows about hydraulics in one big document. And the evolution of this document is an interesting one, because it is an evolution of how a law gets formulated. Henry Darcy, in fact, came from the École Polytechnique in France and in Paris, actually, and that was a very rigorous school. They emphasized the fundamentals and everything. And then, basically, the la crème du crème from that school is actually taken into a very applied program, applied at that time. And that school that he later applied to was called École des Ponts et Chaussées, meaning the roads, bridges and roads, ponte, road, bridges and roads. And that was very much of an engineering program at the time. But the luminaries in that program are by no means small. You have Pitot of the famous Pitot tube, a graduate of that school. I'm putting here a list because there are so many that I'm just highlighting few names that I recognize myself. Chésy of the open channel flow, Chésy equation. Chésy actually also worked with Henry Darcy later in open channels. Navier of the famous Navier-Stokes equations was a product of that school and an instructor at that school, and he actually was an instructor at the time. Darcy was a student there. Coriolis, who you probably have heard of, yeah. Bazin, who was also working with Darcy at the time. Bélanger, who worked on the hydraulic jump, basically. So the Bélanger equation is very famous. It was the first time it was discovered that if you go from supercritical flow to subcritical flow, you do that through a non-gradual way, through a hydraulic jump that produces a lot of turbulence that dissipates excess energy. And in fact, Bélanger was among the names of people listed on the Eiffel Tower. So I don't know how many of you know that if you look at the Tour Eiffel, the first level of the Tour Eiffel has the inscription of 72 names of scientists. Many of the people on this list that I've just mentioned are encrypted, but not Darcy, unfortunately. He should have been. But Bélanger is, Cauchy is, Navier is, so you get this. So this was the training that Darcy did. And in fact, Darcy ended up having to confront a serious engineering problem. The city of Dijon, which is well known for its good mustard, incidentally, had the worst water quality problems, actually, in probably Europe. And it had also sanitation problems that we don't want to discuss too much. So, but it was the birthplace of Darcy, and he was committed to fixing this himself. So he started work on the rapid sand filters after exhausting the possibility of actually using groundwater from the start. Darcy's book, actually, Les Fontaines, did a lot of research on groundwater, but he decided then that the best option for the city of Dijon was surface water. Now, how do you treat the water? So the design of rapid sand filters was necessary, and it was an innovative idea because at the time, a lot of engineering research did not even consider too much energy losses. So what was new about Darcy's thinking at the time is that hydraulics and hydrodynamics were almost two separate fields. Fluid mechanics actually was born out of the merger of the two. But hydraulics was a very applied empirical field. It was primarily a collage of data and experiments, whereas hydrodynamics was dealing with ideal fluids. And what was known from ideal fluids is that the energy was conserved. So the idea of energy losses was a little bit mind-boggling at the time. And if you look at Les Fontaines, Darcy's work also was first to establish energy losses in open channels. In fact, we now have a friction factor called the Darcy-Weisbach friction factor that emerged from these studies. And it was that research that also gave him some foresight that the movement of water in porous media is driven by energy gradients. So there must have been lots of losses. The problem with Darcy's era is that a lot of the studies were done with uniform flows. The cross-sectional area of the pipe, the section that was used, or the soil column was constant, the flow rate was constant. So all the energy losses were typically either pressure or gravitational. There was no losses that are based on kinetic energy because the velocity was the same. So there was no way to think even outside the box and say, oh, these energy losses ought to be driven by velocities. They were primarily assumed that if the head loss is described by a pressure potential and the gravitational potential, how would energy enter into the picture? Kinetic energy meaning, yeah? So some of these ideas were in very, so to speak, hazy at the time, and in fact, Darcy was able to put all of these together in a coherent picture and come up with this analogy. So again, so what are the energies that drive the water movement? So of course, to use Darcy's law, we need two things. We need to know the energy so that we can compute the energy gradient and the hydraulic conductivity. So what I'm going to do now is briefly touch upon how we compute energy in soils and how we compute hydraulic conductivity. And again, why are we doing that? Is that to close the flux, we need to link that flux to the state variable that we are interested in, which is volumetric soil moisture content. So somehow we have to link the hydraulic conductivity and the energy to volumetric soil moisture content. And that was the driving factor of a lot of research after Darcy's law, how to do that. And basically, we can start with Bernoulli's definition of total energy, which is the kinetic energy head. That would be V squared over 2G. So that's the head in water. So, you know, in soil physics, rather than deal with energy units, we like to deal with equivalent head of water, but the two mean the same thing. Then so we can break the total energy into kinetic and potential. The potential part has a gravitational potential and the pressure potential. The gravitational potential is easy to understand. You know, if you lift, let's say, an object against gravity, yeah, you gave it potential energy. If you let it go, you could convert this potential energy to kinetic energy, you know, if it goes with gravity. Okay, so that's easy. The pressure potential is an interesting one. We can understand it in a positive pressure sense. Yeah, you have a piston filled with a gas. You push the piston, you let go. The piston can do work and push. The gas can do work and push the piston back out. Okay, so that is a form of work that is often pressure potential. But in the case of unsaturated soils, in fact, you have to exert energy to pull the water molecules, yeah, out of the soil system because of a phenomena that is connected to cohesion and adhesion with it. Okay, Wilfried has hinted a little bit at this in the xylem of the plants. In the soils, the pressures are also quote-unquote negative because you have to do work to get molecules of water out of the soil particles because the soil particles like to adhere, the water particles like to adhere to the solid surface, and you have to do some work to pull those water molecules out. Okay, so this is just simply a repeat that the gravitational potential is associated with where you are. So often you have to have a certain datum to compute them. It's you know, work against or with the gravitational acceleration of the Earth. However, this is just for the notes. The pressure potential, which is the second part of the kinetic energy, which is the second part of the total energy, is not easy to compute. Okay, so I will now mention it, but just let me say this: that in the case of soils, we shall see in a minute that the velocity head is very small. So really, the total energy is going to be driven by these two. Okay, and we will make an argument as to why. Okay, so the pressure potential in unsaturated soils, well, it typically arises from two properties of water, in general, actually liquids, adhesion and cohesion. So just to clarify what we mean by adhesion and cohesion, well, as they suggest, you know, adhesion has to do with intermolecular forces. This is what keeps the fluid together. In the case of cohesion tension theory, the reason why the column of water does not adhesion is what is actually attached to the solid surface. Cohesion is what keeps the water column from fragmenting. So adhesion basically is the desire of water molecules to attach themselves or to bind themselves on a water surface. This is actually what generates the no-slip condition in fluids. Cohesion is actually what keeps the water column holding together, so it blocks it from fragmenting completely. And in case of plants, cohesion tension theory is basically when you get loss of water molecules by evaporation, as Wilfried mentioned, that you have to pull the entire column of water up by one molecule, yeah, of water, and that generates the tension in the column. And so basically, because of cohesion, because of these attractive forces between water molecules that keeps the film together, the water film can handle tension. But adhesion has to do with liquid-solid interfaces, and it is the desire of liquid to bind on the water, to bind on the solid surface. Okay, so basically, the pressure gradient now that we are going to discuss is the interplay between adhesion and cohesion. And that actually interplay promotes the formation of a meniscus. The menisci is the Greek word for crescent. And often than not, the concavity of that meniscus, whether it is concave up or down, simply reflects which is stronger, adhesion or cohesion. And I should also say, as Wilfred has mentioned, it takes a certain amount of work to break this meniscus and allow water molecules to escape. So for example, in the case of, let's say, water in a glass tube, you find that the meniscus is more like that, whereas in the case of a mercury in a tube, you find the meniscus is like this. And why is that? Okay, well, you could see what happens is that in the case where adhesion exceeds cohesion, then there is a tendency for these water molecules to almost attach themselves to the solid surface, yeah? And so this attachment actually pulls the water molecules up, and they're still held together by adhesion. But because the cohesion basically is here, and the adhesion is here, the tendency to absorb on those particles is basically there, and the film gets attached like that. So you get this one. Whereas adhesion is, in the case of a mercury, is less than cohesion, and so the opposite happens. The film, the molecules tend to be reflected a little bit away from the surface, and you get the curvature to be more like that. Okay, so basically the adhesion-cohesion arguments simply dictate the meniscus shape. But in terms of forces, which is what we are ultimately interested in, is that if we have water and we have surface tension, and we reach a certain equilibrium where the surface tension now is carrying the entire weight of the column. So if you project this force here, and the surface tension is shown here, you get that the weight has to be balanced by rho, the density of the water, multiplied by the gravitational constant, multiplied by pi r squared h. So that's the weight that is actually going to try to dissipate the surface tension. And what is holding this weight together so it rises in this tube is going to be the surface tension force, and that is simply 2 pi r, yeah, so it is applied on the surface area, multiplied by sigma s cosine of omega, which is this angle here. So the surface tension basically becomes 2 pi r sigma s, the surface tension force, multiplied by that angle, and that contact angle depends on many things. But the important result for us is that if we equate the surface tension, which is here, against the weight, so this is a force balance in the vertical, you find that how high the water will go up is inversely related to the radius and directly proportional to the surface tension, and of course inversely related to rho g. So this height is dependent on surface tension and the radius of the tube. Okay, so what is important then to us is that it seems that the ability of water to rise, yeah, in a tube, which is also a reflection of how much energy in the soil when it is negative, you need to apply to get rid of this binding desire of water molecules on a solid surface, is going to be inversely proportional to the size of the tube. And that almost makes sense. I mean, imagine you have a sponge, let's say. If the sponge is very porous and it is saturated, a little bit of suction will allow you to get a lot of the water out. But if the sponge has a very fine textured pore system, you will have to apply a lot of suction to get the water out. I mean, don't do this with soap in your mouth. But you could get a feel for how much energy it will take. Yeah. So the important then point here is that the amount of energy you need to apply, yeah, to overcome surface tension is going to be inversely proportional to the radius of the tube. Okay, so this is an important argument because this primarily applies for unsaturated soils. So in other words, you want the soil particles to be bound on the soil. You want the water molecules to be bound on the soil particles, and basically this is the amount of energy you will have to apply to get them out. But if the soil is saturated, then you don't have that problem, yeah? Because basically you have almost positive pressure in the soil system, not negative pressure. Very much like hydrostatic, basically, like you jumping in a lake as you go deeper, the weight of the water on top of you dictates the pressure, right? Similar arrangements happen if you are dealing with groundwater flow, which is completely saturated. So if all the pores are connected, yeah, and they're filled with water, then you basically experience the equivalent of hydrostatic pressure. But if you have a lot of gaps, basically you have to pull the water against the adhesion, yeah, to get the water out, or surface tension. Okay, so now what we would like to do is show the difference between Darcy's law and the other laws. What makes Darcy's law a little bit different than Fourier's law or Fix's law or whatever. Yeah. So to do that, it might be a good starting point to look at the Navier-Stokes equations. This has been covered by many lectures so far. So you have the local rate of change, the advective rate of change, the pressure gradient, the gravitational term, and the viscous terms. So these are basically the basic, this is the acceleration part, this is the forces acting on the fluid. Okay, fair enough. So what is the connection with Darcy's law? Well, to get Darcy's law and see its connection to the Navier-Stokes equations, what we will do is start by assuming the flow is steady, so we butcher this term. We will also assume that the flow is low Reynolds number, and actually John gave almost the identical argument to this. So if you take the viscous term, you divide the inertia by the viscous term, so this term versus this term, and you assume that you have a characteristic velocity and the characteristic length. This term ends up scaling as velocity over upon length, so you get u squared over L, and this term ends up being viscosity, velocity upon L squared. So you end up with a characteristic Reynolds number, which is velocity L divided by viscosity. So if this quantity is much less than 1, you could ignore this term relative to this term. So you throw away this term. So you're left basically with no acceleration. Okay, so that's the first assumption in Darcy's law, is that there is no visible acceleration. So you end up with almost a balance of forces between the pressure potential, the gravitational potential that only acts in the vertical, and the viscous term. Up to this point, this equation is written for the fluid part, but we're not interested just in the fluid part. We would like to know the velocity in the porous medium, yeah? Darcy's law is going to be a flux of water in a porous medium. So how do we then bring in the effect of the porous medium on the fluid? John already mentioned that in the problem of canopy flows, you spatially average, right? You apply a spatially averaging operator. And that's what we're going to do. So we're going to apply a spatially averaging operator to the simplified equation, because we would like to consider the effect of all the solid grains, yeah, on the water movement. And here we're going to assume that our spatially averaging operator is at least comparable to the representative elementary volume, whatever that representative elementary volume is. So we do that, and we apply the volume averaging operator, which we are indicating here by these brackets. So you end up with the average of the pressure gradient is going to be balanced by the viscosity multiplied by the average of this term. So this problem now at this stage appears intractable, because to compute this term, you need to know the viscous stresses on every single grain in the soil system, which is impossible. So we need to somehow get rid of this problem and replace the effect of the, so to speak, viscous forces on all these grains with something else. And so we have to resort to some phenomenological model, and we're going to do exactly what John did for canopy flows. We're going to represent them with a drag force. Same argument, yeah? So this is just for your notes, that the problem looks like a balance between a pressure gradient force flowing through the pores, and it has to combat basically, or resisted by the viscous stresses. But those viscous stresses are only acting on the contact area between the solid grains and the moving fluid in this control volume. So now we're going to choose an effective drag force analogy to basically eliminate the complexity of the viscous stresses and lump them basically all into this drag force. So now we envision that the viscous stresses, very much like John has done, but for the other term, in fact, is some anisotropic drag multiplied by the area divided by the volume, and this would be basically the area is what is exposed to the drag force, yeah, within a volume of soil. So that is why this term is here. This would be almost like a drag coefficient. This is the magnitude of the velocity, which is low, but still, this is what is causing the shearing between the fluid and the solid, and this would be the velocity vector. So if you want it to be somehow, this is not entirely clean, but it's tensorially correct, okay? So with this, now the challenge becomes, can we derive some formulation for the drag? And here we assume that if the flow is at sufficiently low Reynolds number, then the drag coefficient along each of those grains is going to be represented by what we call a Stokes law. So that would be inversely related to the Reynolds number. And this is a graph that shows the drag coefficient as a function of the Reynolds number for circular disks and for spheres. And you could see that at very low Reynolds number, the linear part is almost the same, not overly sensitive to the geometry. The geometry kick in as you start going to higher and higher Reynolds numbers. So the difference between a circular disk and a sphere becomes quite different. And in fact, even for a sphere, if you have a smooth sphere versus a rough sphere, you get some differences at higher Reynolds number. But at lower Reynolds number, it seems that the drag coefficient as a function of Reynolds number is pretty insensitive to the precise geometry, okay? The geometry becomes more severe as you go to higher and higher Reynolds number. Okay, and of course, if you continue to increase the Reynolds number, you get phenomena like separation, and so the drag might drop, and all of that good stuff. Okay, but now we are concerned with the low Reynolds number phase, so we're going to represent the drag coefficient as some inverse of the Reynolds number. So to do that, we will argue that the drag coefficient is simply some constant that depends mildly on the geometry against the Reynolds number, and that constant then is to be determined from experiments, because we don't know exactly all the geometry of the pores, right? The solid objects. And then the Reynolds number is nothing but the velocity multiplied by the length over the viscosity. So if you do that, and you take this expression, plug it back here, right? One of those velocities is going to cancel. And so you end up with the linear drag coefficient, meaning that the viscous force scales with the viscosity, scales with the soil porosity, and that comes about because there is this area to volume. And then you introduce a permeability tensor, and that permeability tensor actually encodes two length scales, so it has units of 1 over length scale. One of them has to do with the area to volume, that gives you a length, and the other one actually turns out to be dependent on the length scale that you use to scale your drag coefficient. So there are two interesting length scales that emerge, even though they're not entirely independent of each other. And then you have the velocity, magnitude. So if you make this representation for the viscous stresses in the spatially averaged Navier-Stokes equation, and you plug it back, you find now that the pressure gradient averaged plus the gravitational term minus our representation for the effect of the viscous forces from every single solid particles on the moving fluid is now given here. Now, if we just, to illustrate, focus on a 1D case, vertical, so we keep the gravity intact. So in this case, you have the vertical velocity is given by a constant permeability, viscosity, porosity, multiplied by the pressure gradient minus the gravitational term. Now, if you multiply both sides by f, you find that the velocity, the vertical velocity spatially averaged multiplied by the porosity is equal to the flux of water, and that is given by the permeability divided by the viscosity times the spatially averaged pressure gradient minus the gravitational acceleration. This is, in a nutshell, Darcy's law with some ad hoc assumptions. It follows the same averaging rules that John has applied. It shows a clear connection between a velocity, or a flux of water in this case, and the pressure gradient adjusted by the gravitational acceleration that only acts in the vertical. And so the unknown that now encodes all the properties of the porous media is hidden in this permeability. And that permeability, if you remember, has to do with two things. It has to do with the area to volume, and it has to do with what is the characteristic length scale that governs the drag coefficient. So these are the two important length scales that somehow encode the magnitude of the permeability. Okay, so you might ask, well, how low is low in the case of application of Darcy's law? And that has been determined somewhat theoretically and experimentally. It has been shown that Darcy's law actually remains reasonable up to Reynolds number that are less than 10 if the Reynolds number is defined by a velocity, which is, in this case, flux of water divided by the porosity, multiplied by characteristic size of the particles, often referred to as D30. This is basically the sieve size of which 30% of the soils will pass. So if you have a mesh, you throw particles soil particles on it. 30% of them pass through the sieve. The characteristic diameter of the sieve then would be d30, and of course the viscosity of the fluid. So if you define the Reynolds number this way, so this d supposedly encodes the dimensions of the solid particles. Yeah. Okay, so this is the reasonable approximation to use Darcy's law over. Now, I should say that what happens if RE is a little bit bigger than 10, but the flow is certainly not turbulent, okay? The flow is certainly far from being turbulent. We can simply say that we might do a minor correction to Darcy's law to allow for a slightly higher Reynolds number, and that has been done by Forsheimer. So the idea is to try to extend Darcy's law a little bit more, because in the case of groundwater flow, especially near pumping wells, the Reynolds numbers are a little bit bigger. If you're interested in the hypheric zone in hydrology, you have a turbulent flow in the stream, and you might have higher than, let's say, Darcian velocities in the porous media next to them. So you could argue that the same terms in the Navier-Stokes might still hold, not quite, but might still hold. But now what we can do is revise the drag coefficient, okay? So now what we can do to the drag coefficient is say, well, if we are away from this linear, and if we keep increasing the Reynolds number, we're going to flatten out. So perhaps this transition from linear to non-linear, from linear to constant, might be encoded in a form that looks like this. So if you write the drag coefficient as inversely related to the Reynolds number, that gives you our Stokes flow. But then you could say slightly higher Reynolds number can be included here in the limit of high Reynolds number. So when BRE is much bigger than 1, you get a constant. Okay? Does that make sense? So this is, again, all of this is, you know, there is the big leaf. This is like the big pour. Okay, so now we have another constant to play with, but what you could do is if you insert this approximation to the drag, so the idea is that you will never reach this constant, but the idea is that if you start deviating, yeah, from linear, these minor corrections that will push you towards a constant then can be handled. And so if you do that and you plug this drag coefficient in the same equations that we have done, you find that the pressure gradient now is given by the viscosity, permeability, multiplied by the flux of water. And then there is a new constant, K prime, that some people call inertial permeability, because there is some inertial effects popping up, multiplied by Q squared. And the origin of this Q squared, or the quadratic term, comes from the constant drag. No surprise. Okay. Okay, so basically this could be viewed as a correction to Darcy's law. So now you have to almost solve a quadratic equation if you know the pressure gradient, yeah, or the opposite. Okay, so fine, and now you have two unknowns, K and K prime, that you have to deal with. so the Forsheimer correction to Darcy's law requires another constant. Okay, so I want to also mention a few things about Darcy's law and the Hagen-Poiseuille equation. Wilfried mentioned this a little bit, that the Hagen-Poiseuille equation actually describes flow in a tube that is laminar. And typically what you see is a parabolic velocity profile in that tube, and primarily the source of stresses are the sides of the tube, right? This is what causes friction. And often if you take the same equations that we have played with, but no volume averaging, yeah, you could prove analytically that the pressure gradient can be related to the flux of water divided by R squared. Now, given the linear relation between the flux of water and the pressure gradient in the Hagen-Poiseuille equation, this looks mathematically like a Darcy law, okay, but it is not. It has the same mathematical structure in the sense that there is a flux proportional to a pressure gradient, but this equation has no volume averaging at all. Okay, it's pretty analytical from Navier-Stokes. So there is no representative elementary volume issues. There is no approximation of some volume averaging and drag and some characteristic drag force to represent the viscous stresses, no nothing. Okay? And so sometimes there is the seduction of showing Darcy's law and the Hagen-Poiseuille equation as if they are the same, but they're not. The assumptions behind Darcy's law are much more phenomenological vis-a-vis the Hagen-Poiseuille equation. Okay, so this is basically just describing these differences here for the notes. Okay. Now, another comment that I would like to mention is that, and this actually highlights the tension between hydrodynamics and hydraulics. If you take the Navier-Stokes equations, yeah, as Euler has done, and you throw away the viscous term, and then you assume you depth average this equation for steady state conditions, you could actually show that for this system, the total energy will be conserved. Okay, so V squared over 2G plus rho GZ over gamma, the specific weight of the fluid, so this is density times gravitational constant plus the pressure potential, that would be constant. And this is actually what Darcy had to deal with, is that there were all these conservation laws that are coming out from inviscid flows that suggest that the energy is conserved, but in fact, everything that is responsible for driving the water is based on the gradients in energy, okay? So this was just a small comment that, in fact, the same equations, when you throw away the viscous term, which is the main term responsible for the creation of Darcy's law, yeah? When you throw away that term, you get basically Euler's equations that are inviscid and would suggest that the energy is conserved across any streamlines. Okay, but now most times in hydrology or plant physiology, yeah, these are all, so to speak, issues for the academicians. In practice, what do you do? In practice, the problem is already giving you headaches enough. So operationally, what is often done is you want to link somehow the particle size distribution of soil particles to measures of the hydraulic conductivity and the energy gradient. Okay, we haven't talked yet too much about the hydraulic conductivity, but we've already touched a little bit upon the drag and the size distribution and so forth. And so you need basically the hydraulic conductivity to vary with volumetric soil moisture content in unsaturated cases. In saturated cases, actually, this becomes a constant. Likewise, you need somehow a formulation that links the energy, the total energy, even without kinetic, the total energy to the availability of water. And that is done actually through two functions, two ad hoc functions. One is called the hydraulic conductivity function, the other one is called the soil water retention curve. So the idea is that to compute H, you need to know the pressure potential, but to know the pressure potential, somehow you have to link it back to the state variable you want to model, which is the volumetric soil moisture content. And basically, what this term measures in unsaturated soil is the amount of energy you need to exert, yeah, to pull the water molecules that are bounded on the solid particles. So you have to overcome the adhesive forces. And often than not, what you find is that these functions are generated from lab experiments. So you take a soil sample to the lab, and you could put it in a centrifuge and spin it, and you could therefore apply some tension on it. And you measure how much water you lose as you increase the tension, and you find that these curves tend to look like that. And of course, you could see the curvature of these curves somehow dependent on the pore size distribution, yeah, the pore size distribution. If you have a wide range of radii, yeah, so you apply a little bit of tension, you empty the big pores first, yeah, based on our surface tension equation. You keep applying tension, yeah, more and more of the water that is now bounded to smaller and smaller particles, yeah, will be harder and harder to extract because it's associated with the smaller and smaller pores. So here, there is an inverse relation between particles and pores. So you keep applying tension, it takes more and more energy to get the water out of the smaller pores, and of course, up to a certain point, your system will crash, or you are approaching the limits of continuum mechanics in general, okay? And basically, that curve, yeah, does have some information about the particle size distribution, yeah? If all the pores are the same, you apply some tension. After a certain tension, you sort of empty the majority of the pores in one shot, so you get a very binary curve. On the other hand, if you have a wide range of particle size distribution and hence pore size distribution, you get a more gradual curve. In terms of hydraulic conductivity, the story is pretty much the same. They are somehow connected to the same property. If your network of pores, yeah, starts dry, you start adding water, yeah, you start filling the pores individually. These water bridges between the pores are not yet connected. You still have a low hydraulic conductivity, and at a certain point, you start getting more connection between the pores, and hence the conductivity increases dramatically. But after a certain point, where all the pores become connected, you increase the volumetric soil moisture content a little bit, no change happens, and hence that's why these curves typically look like that, okay? So these are on a semi-log axis here. So of course, now what we could do is, there is some connection between the particle size distribution, the pore size distribution, and the curvatures of these functions, what is done in practice is to try to put it all together through some empirical relations. And those have been studied extensively in the literature. I'm picking here one example, and that example is used in many climate models now. So it basically classifies the soil based on its percent sand, silt and clay. And for these percentages of sand, silt, and clay, you could come up with 12 groups that go from sand, loamy sand, sandy loam, silt loam, etc. So these are simply just different percentages of sand, silt, and clay. And for disturbed soil samples that were taken to the lab, the functions that we have been dealing with, so this is the pressure potential as a function of volumetric soil moisture content, how much energy you need to apply to get that volume of water out of the soil particles is given by a power law. And because these are not 100% saturated, so they're often represented by some near saturated pressure, multiplied by the volumetric soil moisture content normalized by this field saturated pressure, if you like, raised to some exponent b, to emphasize the fact that increasing volumetric soil moisture content reduces the amount of energy you need to get the water out of the soil particles, soil system. And likewise, the hydraulic conductivity is dependent on some saturation value that you would approach if the pores are all filled, and now the network is operating, the network of pores is operating as a monolithic unit. So you have a Ks, saturated hydraulic conductivity, multiplied by the same ratio, which is theta divided by how much water you could saturate the pores in field conditions often, because you can never really saturate them all, raised to the 2b plus 3, with the assumption that this b and this b are the same. So these are disturbed soil samples. And what you find is that for different configurations of sand, silt, and clay for disturbed soils, the theta s, which is kind of like a field porosity, there is a mistake here in the table. For I hope the climate community is not using this value. Well, you never know. This was literally taken from a table that they published as to what they're using. This would be roughly the pressure near saturation, not exactly at saturation, that's why it's somewhat small. This would be the saturated hydraulic conductivity multiplied by 10 to the minus 6 meters per second. This is the curvature parameter B, so as you go from sand, it's small, you go to clay, it's becoming larger. And often than not, sometimes the wilting point associated with a certain soil type is also published. So basically, in operational models, you have a soil map. You look at the soil map, you identify the percent sand, silt, and clay, and you pick, perhaps, what would be the best representative parameters for theta s, b, psi s, and ks. Now, of course, these are plotted on a logarithmic axis, incidentally, so sometimes just the spatial variability of these quantities may be up to factors of 100. Usually, ks alone has a log normal distribution in space. So you could see the challenges that are confronting the soil physics community. So even though you may be putting one number here, in fact, the spatial variability of those quantities is huge. No surprise if there are roots, if there's a little bit of more soil compaction. How accurate are really your soil maps? These are disturbed samples, they're not intact. You disturb the soil samples, you are disturbing the pore structure, period, yeah? You are not taking an intact pore structure, which is so crucial to definitions of retention curves and hydraulic conductivity. So this is the problem in soils, in a nutshell. Okay, but operationally, once you have a relation between Q and K of theta from Darcy's law, and you are able to link the hydraulic conductivity and the soil water retention to the state variable, volumetric soil moisture content, through these curves, mathematically, you have closed the problem. Mathematically, you have closed the problem. In reality, you are still far from accurate predictions, but you could still do some tests, okay? And so now, to make the story more interesting, what we're going to do is introduce roots. And for that, I'll just now take a short break, because this would be a good point to stop, and then we will pick it up again. We still need another half an hour. Okay, so the second part of the talk is just to briefly introduce the role of plants in soils. Before we jump into this, I simply wanted to say that even in the case of pure soil, first without plants, you need to know the boundary conditions, you need to know the hydraulic properties, meaning the soil water characteristic curve and the hydraulic conductivity function at all the soil layers. You need to know the initial volumetric soil moisture content profile. You need to know something about the drainage in 1D. In 3D, of course, you need to know what's happening on the sides of the box. So all of them have to be specified if you're just interested in water movement in soil in the absence of plant water uptake or root water uptake. Now, what we're going to do is briefly touch upon those and then try to proceed with the root water uptake. But what we're going to do is vertically average these equations. So we look at the bulk relations first, and then we look at everything together when we put the root water uptake much more mechanistically in those types of equations. But I would like to also discuss a little bit qualitatively what happens in terms of root water uptake and boundary conditions playing, so you could depth average this equation and see what happens in a continuity sense. Okay, so to do that, to start just looking at the presence of roots without too much details of the soils that we have been covering, and try to handle the variability in rainfall, but mediated by the fact that water can be stored in the pores of the rooting system, we might look at what the electrical engineers often call impulse response. So we envision the precipitation as our impulse. We envision our fluxes as a response. Okay, and so to do that, and I'll say in a minute why this is important, we're going to look at a case study in terms of volumetric soil moisture content data from Duke Forest. And the reason I picked this example is that if you're thinking about the project for Friday, this is an easy one to do. All you need to do is compute few spectra, as you will see in a minute. Now, the reason this is somewhat important and the reason atmospheric scientists initially took interest in soil processes is that the soil, because it can store water, it can maintain its state for periods of time that are way longer than the changes in atmospheric processes. So typically, the memory of water or the residence time of water molecules in the soil system may be, tens of days, whereas the passage of storms, boundary layer dynamics, are occurring on timescales of half an hour to few days. So the fact that the soil moisture state, retains its value, for a long periods of time compared to the fast atmospheric processes means that there is basically a considerable impact of soil moisture content on whether the atmosphere remains wet or dry. And so that's an important point to consider. And in fact, Manabe has taken quite a bit of interest in this in the late 60s. And we are going to touch a little bit on the original Manabe analysis and few revisions to it. Okay. Now, this theme keeps playing prominently in the climate system. This is one example of a paper by Randy Koster from the Glacé team at NASA, where they were trying to map, basically, come up with a global map of regions of strong coupling between soil moisture and precipitation. Because of this memory, wet states tend to maintain some wet states in the soil, and that has some impact on the atmospheric humidity. Atmospheric humidity means that the lifting condensation level is pretty much set by wet soil moisture states, and so you could actually induce precipitation when the boundary layer height crosses this lifting condensation level. And so what Randy and his group at the Glacé team ran a whole bunch of GCM runs to try to find regions in the world where they thought that the volumetric soil moisture content and precipitation are tightly coupled. And they were viewing that those regions have, so to speak, hotspot status, because if you do a lot of land cover conversion there, you may be altering the hydrologic cycle dramatically. So that is the interest in the climate community. At the same time that these results were popping up, there were assemblage of large data sets by Alan Robock, where a data set from China and the Soviet Union, where almost on a 2-week cycle, volumetric soil moisture content was measured at a huge number of stations, and Alan Robock was able to compile all of that in a global soil moisture data bank that was published in the Bulletin of the American Meteorological Society. And a lot of people analyzed this data bank, as well as other data sets, primarily from the Illinois network. And if you summarize the main findings from these papers, some are pretty obvious, but good to see in data sets. One of them was that the amplitude of soil moisture variations decrease with depth. Well, no surprise. Of course, soil moisture is going to vary closer to the surface because you're seeing precipitation and evapotranspiration most there. If you go to the deeper layers, it's completely buffered, very much like heat flow. So that's not a surprise. The fact that soil moisture memory across various geographic regions increases for drier states when compared to wetter conditions is an interesting one. So they're saying that drier states tend to persist longer or stay longer in that state compared to wetter conditions. And then another one that was interesting is that the soil moisture is generally in phase with precipitation at long timescales, but seems to be out of phase at short timescales. Why is that? Why should precipitation be and soil moisture content be in phase for very long timescales, but not very short timescales? They seem to be opposite. So to try to come up with an explanation for these, at least qualitative findings without the specifics of a site, we decided to look at the hydrologic balance with an eye towards trying to understand how these things pop up, how these conclusions might pop up. So this is exactly the point. We're going to now present a qualitative analysis that shows the links between the spectrum of soil moisture content that encodes a lot of these conclusions and rainfall. And to do that, we used our in-house data set, and I have that data set if you yourself are interested in playing around with it. This is a public data set. It's an 8-year data set of 30-minute, spatially averaged and depth averaged volumetric soil moisture content within the root zone. And with this data set comes precipitation, throughfall, or at least estimates of throughfall, and eddy covariance-based evapotranspiration measurements. Now, the theoretical underpinnings behind this analysis starts with the depth integration of the conservation equation for mass. If you do that, basically you have input flux, output flux, that either has to be modeled now with the depth integrated stored water here, or if there is no flux, it becomes zero, so you have something like a clay pan or a bedrock or whatever. So that drainage flux becomes small. And of course, then the water losses are going to be through evaporation and transpiration. So if you write a mass balance equation, which can also be derived from the continuity equation we started with by depth averaging it, you find that the change in stored water, let's say within the routing zone, and in this case we're assuming the routing zone depth to be constant, is going to be whatever throughfall occurs minus whatever evapotranspiration, and if there is finite drainage, that is going to be accounted for as well. And the soil in this case will be characterized by some porosity eta. Now, the losses themselves can be lumped into ET and drainage. And for non-dimensional purposes, it's always good to deal with dimensionless equations. We're going to normalize actually the stored water by the porosity and the routing zone depth. So basically, this quantity can go from 0 to 1. And so now the dimensionless conservation of mass would simply say that the rate of change of water stored in the routing zone is the losses divided by the normalizing variable, and that has to be balanced by the input to the system, which would be throughfall. And of course, throughfall then can be linked to precipitation. So again, we have, even if we know all the statistics of precipitation, to predict the statistics of the water stored in the routing zone, we need some information about the losses. And so how do we get that? Well, we could, I think I decided to show the experiment first. So this is where the data comes from. This is the free air CO2 enrichment experiment at the Duke Forest. It comprises of actually 6 rings and the prototype ring here. And in each ring, there are 4 time domain reflectometer rods that are measuring volumetric soil moisture content every 30 minutes. And that's a data set that was compiled over 3 generations of graduate students, so not trivial. Yeah? So it's 8 years. And so yeah, every single graduate student during that era had to pay their dues by maintaining that data set for a while. Okay? But at the same time, there were throughfall collectors. There were also sap flow measurements. The volumetric soil moisture content was measured like that. And there were eddy correlation measurements of turbulent fluxes, including water vapor at one of the towers. And so basically, the data set is spatially averaged over all the rings and all the rods. And this is how it looks like over the 8-year period. This is precipitation as a function of time. And here, time is shown in days. This is the measured evapotranspiration from the eddy correlation, gap filled, and everything. And this is the spatially averaged volumetric soil moisture content every 30 minutes. And you could see roughly that when it rained, it was going up and down and so forth. And so there is a huge variance in volumetric soil moisture content during this period, as one might expect. Now, at this site, the reason this was optimal for the analysis here is that while precipitation was high, it was about 1,280 millimeters per year, interception was about 40%, and ET was about 650 millimeters per year, and that was roughly measured by the eddy correlation system. So if you like, ET to throughfall was about 85%. And so basically, we reduced the precipitation based on throughfall, but the throughfall, at least at that site, when you look at daily timescales, it's roughly constant. Okay, fair enough. And then the drainage losses were trivial because we were able to close the mass balance without having to invoke too much drainage. So we, for purposes of simplification, we dropped it. Okay, but that doesn't help us. We still need a model that links evapotranspiration to volumetric soil moisture content. And what we did is we said, well, there are many possibilities. You know, you could start with a maximum evapotranspiration at full saturation and simply go linear. So as the available water drops, the evapotranspiration simply drops relative to this maximum. You could go through nonlinear features, or you could have a threshold phenomena. You could go constant, 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 and then crash linearly beyond a certain volumetric soil moisture content. Now, I'm going to start by first featuring the analysis on the linear part and simply tell you what the nonlinearities will do. And the reason we can do that is that the linear part has a clean analytical solution that has been known for about 100 years now. Okay? Meaning that if you write your mass balance equation as the rate of change of stored water in the routing zone, plus some losses that vary with the state variable multiplied by the state variable S, is the precipitation, or the throughfall, to be explicit, divided by the stored water in the routing zone. And this beta 1 here is nothing but the maximum transpiration rate normalized by the porosity of the soil and the routing depth, times some function, times some function of the state variable. So that would reflect different models here. If this is constant, if this is set to 1, then basically you have the linear model that simply drops maximum transpiration all the way down to 0 as volumetric soil moisture content drops. Okay. So to do that, first then you could Fourier transform this hydrologic mass balance equation. And after you do a Fourier transform, you basically apply the equation by e to the IFT. You then integrate from minus infinity to plus infinity. And then you could derive an explicit relation between the spectrum of volumetric soil moisture content and the spectrum of precipitation. Here, P of f and E S of f are simply the square of the Fourier modes. And you find that the relation between the two ends up giving you an f squared in the denominator. This is the frequency. And then there is a constant beta 1 here that depends on the loss function itself. So ET max divided by eta RL. So this can be derived readily. And basically what it means is that the spectrum of soil moisture stored water in the routing zone depends on the spectrum of precipitation. It depends on f squared and beta 1 squared. So f squared suddenly appears explicitly here. And it does suggest that if the spectrum of soil of precipitation is entirely random at all scales, you get what is called a Lorentzian spectrum, meaning it decays as f to the minus 2, which is called the red noise, at high frequency, but it is constant at very low frequencies. And that's nothing but simply using this equation, Fourier transforming it, calculating the squared amplitudes. And then what we're going to do now is use a realistic spectrum of precipitation and see what's going to happen to the spectrum of soil moisture content based on these expressions. Not only you could compute the stored moisture content spectrum, you could also compute the phase shift between precipitation and volumetric soil moisture content. And if you do that from this very simplified model, you find that the phase shift is the arctangent of frequency multiplied by the routing zone depth multiplied by the porosity divided by ET max. And that's an interesting result, because if the routing depth increases, then you increase the phase difference between precipitation and soil moisture. And at long time scales, f goes to 0, so they become in phase. So there goes the problem that we started with. It's easy to see now what's going to happening. And at the same time, if you lower ET max, rainfall and soil moisture content, so if this becomes smaller, this difference becomes bigger, they become more and more out of phase with each other. And all of those qualitatively are consistent with the phase shifts that have been discussed in a separate paper that came out from the Illinois Climate Network of Volumetric Soil Moisture Content shown here. So this basically explains everything. You don't need a very complicated loss function. A linear loss function basically with stored water is enough to explain a lot of the key results from the global network of soil moisture content and its variations. So there is no surprise. Everything can be predicted almost from linear theory. But we want to do more. We want to see how good these calculations can be, at least at a site where we know a lot about. So to show that, this is a graph that shows the spectrum of evapotranspiration on the y-axis as a function of frequency. And you could see here the diurnal, the daily, and the seasonal, if you like. And sure enough, no surprise, there is, of course, spikes at these two frequencies. And then basically the ET does not vary a lot, and then at seasonal timescales where leaf area index is varying and so forth, radiation is varying a lot, you see that ET spectrum increases in activity at lower and lower frequencies. In the case of precipitation, you find that there's a whole range where the precipitation looks almost flat, so white noise, but then as you start approaching the storm timescale, which is maybe a few days, there seems to be some structure to the precipitation spectrum, meaning that there seems to be a little bit of a power law that describes the frequency shifts of the precipitation energy decay as a function of frequency. So as you go to as you go to higher and higher frequency, the rainfall is no longer random, but it's becoming more structured. Remember that if the spectrum is decaying, it means that the process is a little bit more deterministic, compared to random, at least, purely flat. Now comes the interesting point, is that if you look at the volumetric soil moisture content spectrum, which is shown on the y-axis as a function of frequency, you find that at high frequencies, at very high frequencies, you have the -2, which we already predicted here. So if F is very large, right, it will overshoot against the B1. So the spectrum of soil moisture content becomes the spectrum of rainfall adjusted by F to the -2. So that gives us the F to the -2. But because the spectrum of rainfall has a structure, F to the -0.75, which incidentally is roughly the average between convective and frontal systems. Convective systems tend to have an F to the -0.5. Frontal systems tend to have an F to the -1. So the interesting thing is that this one is in between. You find that the spectrum of volumetric soil moisture content seems to decay as -2.75, with the -2 coming from the linear analysis that we have done, and the -0.75 coming from the fact that the precipitation spectrum is not random, but is structured. Okay? And then, of course, now the question is, can we reproduce the spectrum of volumetric soil moisture content strictly from the spectrum of precipitation with the simplified model that we have adopted for ET, realizing that the simplified model does not capture any of this variability? And this is actually what you get if you plot the frequency multiplied by the spectrum of volumetric soil moisture content as a function of frequency. You find that the measured values are shown in dots. If you assume that the rainfall is entirely random, you get the blue model here. And if you actually use the measured spectrum of precipitation, you get the red model. And for sure, the high frequency decay is reasonably captured, as we have just shown, up to a certain point, and then the low frequency decay is not. In fact, you see that there is much more activity coming in the measurements than what precipitation can predict. And again, no surprise, radiation is varying, leaf area density is changing. Of course, there is more activity, affecting volumetric soil moisture content than what rainfall alone would do. But the interesting thing is that you could predict roughly the memory, which is now associated with the peak of the pre-multiplied energy spectrum here. And if you do the calculations, it turns out to be roughly about 45 days. And that can be reproduced if you assume that the measured maximum evapotranspiration rate was 0.9 millimeters per hour. The porosity was about 0.55. And in this case, the rooting zone depth to the hard clay pan at the Duke Forest was about 300 millimeters. So in fact, you could show that the memory, at least by this model, is reasonably captured, which means that if you have a soil moisture time series, you could predict, and you know the rooting zone depth, you might be able to predict the maximum transpiration rate associated with it strictly from the spectrum, which is an interesting result. Okay, so what are the implications to climate models? Well, if the soil moisture memory is on the order of 45 days, which is much bigger than 12 hours, that tells you that yes, of course, the overall variance in soil moisture content is important, and that might have some signatures in terms of how much precipitation can feed off on the wet soil or the dry soil. Also, the 45-day memory is much larger than those of many atmospheric processes. Hence, climate anomalies can be sustained through the land surface feedbacks, primarily because they can feed off on this long memory. And I should also say that the fact that the soil moisture content is decaying so fast, it means that if you are looking for hydrologic balances on daily and longer timescales, and you ignore the sub-daily timescale, just for the purposes of computing the stored water in the rooting zone, it may not be a horrible approximation, because, of course, if this is decaying very fast, it means that the high frequency is not contributing a lot to the variability in soil moisture, and a lot of it is residing in low frequencies. Okay, so this is basically what I wanted to say here. And now the last few minutes is just to put a more realistic root water uptake. This has been a coarse analysis. Now we can actually look at the layer-wise averaged Richards equation. Now we model the roots as a function of the pressure difference between the roots and the soil. We have a leaf pressure that is dependent on the transpiration rate. So now we can couple leaf pressure, transpiration rate, and root pressure all together. And then we try to run these calculations in 1D and 3D and try to understand what the rooting system is doing to volumetric soil moisture content. And therefore, what we will do next is we will put two trees next to each other and see how competition for water between two trees affect the overall dynamics if we were to simplify it along a bucket model like we have just done. And the reason this is becoming important is that there was a kind of over the last 20 years or so a resurgence in interest in hydraulic redistribution, or some people call it hydraulic lift. The word redistribution is better because it can go laterally as well as vertically. And what the review by Newman and Cardone summarized a lot of the magnitudes of the hydraulic lift, meaning that if you have a fixed root pressure, you have dry soil at the top and wet soil at the bottom. Water can go from the wet soil to the roots, but if the roots cannot store much water, then that water will have to come out from the rooting zone into the dry levels. And that is basically a hydraulic lift phenomenon. But the opposite can be true. You could start with a very wet soil and push water down into the rooting zone in a 1D framework. And in a 3D framework, in fact, you could have also water moving to the center of the roots or away from the center of the centroid of the roots in a very similar process. In fact, actually, if you look at the rooting zone, the concentration of the roots in the center tends to be high, and the only way you could bring water into this rooting system is through this mechanism itself. So you could avoid the overall depletion of the rooting zone in the center. And this is just one calculation that shows the modeled root water uptake for a linear root density profile, an exponentially decaying root density profile, and a constant root density profile, just to show you how the distribution of roots, same amount, impact the root water uptake. And on this graph, you just see photosynthetically active radiation as a function of time. And on this, you will see the modeled root water uptake. And so if you do that, you see that there is very little activity. There is some hydraulic redistribution happening already. Yeah, so water is coming from wet to dry. It is wetting that much more intensely in the exponential. And then, of course, during the day, root water uptake is the dominant process. And very different, yeah, between the different rooting densities. And then as you go towards the night, we still get back again. Now you see this shrinkage here. Water is leaving from here and wetting the top layers of the soil through hydraulic lift in particular in this case. And this hydraulic lift is intensified for an exponential root density profile versus a linear or a constant. In fact, Mario Siqueira then did a very thorough analysis on this problem, and actually showed the impact of hydraulic redistribution and hydraulic lift on root water uptake for many cases. So he plotted volumetric soil moisture content on the x-axis and transpiration on the y-axis. So it looks like a bucket, and the volumetric soil moisture content is depth averaged in this case. And he showed that if you fix the soil type and you vary the root density, primarily the power law or the exponential in this case, if you include it, yeah, you delay the onset of stress way more than the other root density profiles. And he also repeated the same analysis for a given root density, but changing soil type. And he actually showed that if you have sandy loam, basically, you delay the onset of hydraulic redistribution versus if you don't. So low hydraulic lift is in dashed, solid lines reflect high hydraulic lift. And so basically it seems that the mechanism of hydraulic lift or hydraulic redistribution is to delay the onset of stress, but still it is not affecting the canonical shape of transpiration as a function of bulk soil moisture content. Okay, so it's not changing that dramatically. I should also end this talk by saying that similar analysis was repeating by Gabriele Manoli quite recently, where he actually studied this competition between two trees. So you have two rooting systems now that either do not overlap a little bit, or are completely smashed against each other, and they have to compete to water. And what he found is that the root water uptake, of course, becomes higher and higher as the overlap is reduced, so they're operating separately. But the hydraulic redistribution, yeah, or the hydraulic lift on a daily time scale seems to be more and more prominent, yeah, and delayed when you have overlap in the rooting densities. Okay, so this was just a general features about the role of root water uptake. And Stefano will pick up today the talk by actually proposing a new way to derive the hydraulic conductivity, the gas diffusivity, the solute diffusivity, the electrical conductivity, and so forth, using basically percolation theory. So one way to now avoid the whole definition of a representative elementary volume is to think of the soil as a porous medium, of course, as it is, but now you could look at percolation properties and try to derive those based on the power law distributions that describe soil structure. So with that, I will stop. Thanks.